Today I'll talk about mostly data science part, but in fact, what we do for Intel Python is tackling in general scientific computing, not only data science. But obviously, data science is one of hot areas, and Python is really one of key languages for data science. You can take any survey on what developers prefer, what languages developers prefer, what they love, what they want to study, and Python is typically among top 3 programming languages, especially for data science. So that's the motivational part why I will talk mostly about Python today, but what I'm talking here generally applies to any language that you use in data science. The key attribute of languages that you use in data science is productivity. You as a data scientist don't want to spend your time on programming thousands of lines of the code. You want programming to be compact, quick, easy to debug. This is where Python becomes really, really useful language for data science. That's the one aspect, the usability, how you can express yourself in data science. But the other side of this usability, you cannot do your data science on a laptop anymore. The data amounts are growing in such a way you have no chance to complete the data analysis on one device. Typically, you prototype on one device, on laptop or workstation, but the next step is to deploy this application at full scale on a really big system that tackles big problem. An example is what we have done in the last few years with Berkeley Lab. What they do, they prepare for next really huge experiment. Essentially, they simulate Big Bang. They study the cosmic microwaves, which is the result of this Big Bang, and analyze tons of data. You cannot do this analysis even on 100 systems. You need thousands of systems to analyze and simulate such huge amounts of data. So that's why they've chosen Intel and Intel CPUs, the proven CPUs that can scale to big HPC problems. The challenge here is this problem is more or less solved in HPC space. You can scale HPC problems to as many nodes as possible. In data science, it's a bit more challenging. And second, they've chosen Python for this type of problems. The reason they've chosen Python, essentially what they say most and many new researchers that come to Berkeley Lab, for them, Python sometimes is the only language they know. So there is tons of code written in Fortran, in C, but that's primarily legacy code. New experiments are done on Python side. So there is a gap or bridge you need to build to connect Python with simulation codes. This is where my team, my Python team, helped Berkeley Lab to scale some of these problems to hundreds of thousands of CPU cores. Ideally, what we want, and some businesses, this is the only way to do, you prototype with Python, and then you deploy the same Python code that scales to many nodes. Just for economic reasons. You cannot afford rewriting the code in new language. You need to hire a new team of C++ developers, of Java developers to deploy this at scale. Some businesses cannot just afford. They need to quickly prototype the code and quickly deploy this code in production. But in production, some other technical matters really important. having the large system is very expensive. You cannot really underutilize this system. You cannot run ineffective code on these systems. You just waste in cycles, energy, whatever else. So high efficiency of the code at large scale is really critical. And Python is known to be not very efficient. Typically, it runs hundreds, thousands times slower than native code, than C++ code or Fortran code. What to do? And the basic reason why it runs slower, or why it runs hundreds times slower. Well, we should remember about modern hardware. When I started programming, it was many years ago, computers were really, really simple. If I need to load the data, data load instruction takes 1 cycle. If I need to add 2 numbers, same thing, 1 cycle. It's not the case anymore. Modern computers, they have a gap between performance of arithmetic units and the performance of memory subsystem. Memory subsystem nowadays is much, much slower. That's why CPUs became really complex to hide this gap between bandwidth of CPU compute units and the bandwidth of memory. So instructions became increasingly more complex, and you need to be aware of this when you code for efficiency. So there are multiple levels of parallelism, like instruction level parallelism. When instructions, they decoupled into micro-instructions, and each micro-instruction can be executed in parallel. This is a way how you can, in parallel, execute load instruction, and while this load instruction is taking place, it takes many cycles. You can, in parallel, do some number crunching. That's an idea behind these complex CPUs nowadays. The second idea, how we can increase parallelism and efficiency, is using vector instructions. I can use 1 instruction to add 2 numbers. Or I can use 1 instruction to add 4 numbers. Which one is more efficient? This is called SIMD, single instruction, multiple data points. If you have many independent data points and you want to apply the same operation, you can do this with vector programming, with vector units. That's another way how you can exploit this parallelism. The next level of complexity is using multiple cores. Many CPUs, modern CPUs, they have more than 1 core. And you can execute in parallel different codes on these cores. So you need some technologies to tell your program to run on different cores, and making sure that what they do in parallel and then combined into a correct result. So there are multiple ways how you can do on this Python level. And then the last but not least, big data problem means data doesn't fit in your memory in 1 node, or even on the storage in 1 node. So you need to do big data on multiple CPUs connected to each other. So you need to be able to do multi-node programming. Oh. So. OK. Let me tell about a different aspect. When we started designing the data analytics acceleration library, it was 2012. We designed it in mind of new data analytics problems that we expected. And one of key ideas is, well, there are tons of different data formats, tons of different data analysis problems. But essentially, if you look at analytics pipelines, you can decouple analytics pipeline into some stages which are typically done in any data analysis. We started we're thinking about data problem not as number crunching, the last stage, training or validation or prediction. Data analysis problem starts how you acquire the data. And you soon realize that data resides not on your data center, not in your computer. Data is being generated typically somewhere outside where the data is analyzed thereafter. And as I mentioned, data analytics problems, data science problems, they contrast HPC problems in such a way that typically the complexity, numerical complexity of your algorithms is linear or close to linear with number of observations, essentially with the volume of the data. It means that data transfer, data copying, data input-output cannot be ignored. This is always your bottleneck. This is always your hotspot, performance hotspot to optimize. So we really started thinking about where the data is being generated, in what format, how this data is then transferred to the device, where should I compute this data, and how this data is then being consumed, what kind of problem I'm solving. And we soon realized there are three different areas. The first is the data source. It typically one device or multiple devices. And then the data needs to be preprocessed. Keep in mind, transferring data is expensive. You cannot transfer raw data from your wearable, from your phone, as is, the raw data. You need to compress this data at least. Sometimes you need to encrypt this data. Sometimes you need to do some filtering with the goal to minimize the amount of the data being transferred. Ideally, you want to analyze this data as close to data source as possible, right? To exclude this expensive data transfer time. And then suppose the only problem with these data sources, devices, they're not computationally powerful. Sometimes you need to perform analysis on a more powerful device. So you cannot ignore the data transfer. You need to account for this. But you also need to minimize the amounts of data being transferred to the device where you analyze. And the last stage is where the data is consumed. Typically, it's your consumer device. It can be a laptop, it can be your phone, it can be something which is, again, may be very different from the device where you train the data or perform some modeling. So with this in mind, we really tried to decouple the problem of data transfer, data ingestion, the protocols, how this data transfer are organized, and the computation. This is really essential for modern software. The other aspect, when we started designing this software, we started thinking in terms of, well, what it really means, what big data really means, what real-time data means, etc. And as I mentioned, big data typically means the data is distributed across different devices. It just doesn't fit into one device. What from computational machine learning library it means? It means that the library should definitely support distributed processing. You can do scikit-learn on your laptop, but when you scale your analytics in big production, you cannot ignore the need for distributed processing. The other aspect, let's imagine, OK, even I have just one node, but my data doesn't fit into memory. Can't I solve this problem? Of course I can. I can solve this problem by using online methods. Online methods mean I don't need to load the full data set into memory. I can read this data and load this data in memory by chunks of appropriate size and then process the data by chunks. So if you are thinking about modern data analytics software, it should definitely support the online processing. Not just for the need for processing real-time data, but even for processing the data that simply maybe not fitting in the memory of one device. Or the other argument for that, again, data input, output, or data transfer is expensive. If you use online method, you always can try to hide this expensive latency of data ingestion by using asynchronous analysis. I load the next chunk of the data, but in parallel, I can do number crunching. That's the way how you optimize this expensive part. So data coming in time, again, you use online algorithms for data analysis. One more attribute of big data problem is typically the data is non-homogeneous. This is very contrasted typical HPC problem. How HPC approach the problem? Well, I have some big data set of doubles or complex numbers, complex doubles. Let's analyze this and do number crunching. With big data, you have a mix of data formats. You may have categorical data, you may have strings, you may have integers, floats. You can say, I can always translate these numbers into a floating point and reduce to HPC problem. Yes, you can, but remember, data transfer is expensive. Data transformation is expensive. You cannot ignore this part. You need to optimize this side too. That's why we put specific emphasis on dealing with non-homogeneous data sets. And the last but not least, typically big data has high sparsity, or there are lots of missing data, or data is noisy. You cannot ignore this. You need to have special robust methods that process noisy data, or deal with missing data. If you remember, typical statistical approach for handling missing data, if I have one of observations having missing data, typically it was ignored. What if you have lots of missing data? Will you ignore the full data set? Of course not. You need to deal somehow to restore these missing values. So you need to have special methods that deal with this too. And the last but not least, I already talked that HPC, they typically focus on this right-hand side, compute and memory. They think all I have is already in memory, everything is homogeneous, let's do the compute, do number crunching. The database world, they typically ignore the right-hand side. They typically focus on how you encode the data on the storage, to minimize the storage, to optimize the query. But that typically come in expense of how you then compute this data. Remember, modern hardware deals with homogeneous data. SIMD registers, they deal with homogeneous data only. So on the left side, you have non-homogeneous data. On the compute side, you have homogeneous data. You need some way to transfer non-homogeneous data, convert this into homogeneous, and then compute. And you do this through memory. Of course, you cannot ignore the memory. And the last argument, depending on data analysis problem, you can still use high-performance language like C++ to do really high-efficient code to analyze close to real-time data. Sometimes you need Java Scala, like you use Spark or Hadoop. Your obvious choice will be Java or Scala. And if you're a data science part, you're typically on Python. So that was one of arguments when we started developing this data analytics library for high-performance data analysis. We started thinking we really need to support all this. You cannot be on the one side, on data science side only. You need to think about deployment side too. So that was an argument to support multiple language bindings. Python binding, C++, for highest efficiency, Java and Scala. So that was essentially the main motivation when we started this Intel DAL project. And this is not proprietary project, it's open source. You can go GitHub and find this DAL project. So we created C++ interfaces, created Java interfaces, created Python interfaces. You can install PyDAL package with any Python you want and use it. So if you remember, when we designed the library, there were multiple design choices. One of these big choices was we need to decouple data transfer protocols from the computation side. So DAL was designed agnostic to any communication. That's, on one hand, lots of flexibility, but it's also, when you implement full solution at scale, sometimes you need to integrate DAL pieces into communication protocol piece. That's a bit too complex and for data scientists. So for data scientists, we created another level of abstraction, which is called DAL for Pi. Essentially, it will provide you interfaces scikit-learn-like. But with DAL for Pi, you can do online and distributed processing with amount of the code roughly the same as with scikit-learn. Remember, scikit-learn and pandas allow you to do in memory only. You cannot do process the data set with scikit-learn, which doesn't fit into memory, right? You have no choice. You need to do something about that. With DAL for Pi, you can easily do computation on any number of nodes with any data size. OK, that was mainly the motivational part and the story of the design. Let's see performance numbers. This is the main part of the presentation. At supercomputing, Intel and Google announced that Intel Python now runs on Google Cloud Platform. And these numbers show essentially if you do machine learning, in this particular case, we've done image recognition, MNIST data sets, and we performed clustering of these data sets, essentially clustering 10 clusters to identify the digits, clusters of digits. Compared to stock scikit-learn deployed earlier with stock Python at Google Cloud Platform, with the scikit-learn that we optimized, and we optimized it using DAL and PyDAL. Remember previous slide. What we do, we optimize scikit-learn using PyDAL algorithms. You can see 20 times better performance. That there is no magic. DAL is designed taking into account performance aspects. SIMD, instruction level parallelism, multi-threading. This is all the design. This is the amount of speed up you can expect if you design your software in an appropriate way from the very beginning. That's another example, a support vector machine classification. Again, the baseline is stock scikit-learn. In our case, 0.19.1. I would say this is the latest version of scikit-learn. And we perform both two-class and multi-class training and prediction. The speed-ups that we see because of DAL optimizations that we apply to scikit-learn range from 5x in case of two-class training to maybe 15x in case of multi-class training. But when it comes to inference part, the prediction is hundreds and thousands times better. And again, the reason is the aspect of performance in mind with the design of Intel DAL. Now about distributed processing. 1, 2, 3, 4, 5 lines of the code. One of them is just import. You perform k-means, you load the data, and you process. The upper one is typical in-memory analysis that you do with scikit-learn. The bottom one is what modifications in the code you need to do to perform multi-node analysis. You can easily install this. It's hosted on Anaconda Cloud. There is Intel channel on Anaconda Cloud. You go and do conda install to get this functionality and play with multi-node data analytics. Performance numbers. Left chart is scalability of k-means. Exactly the code that I've shown on the last slide. So we use 1, 2, 4, 8, and 16 nodes. Each node has 2 sockets, and each socket has 20 cores. So that's quite a large system you can expect. And what we can expect. So we use 2 processes per node. We fixed the data set size to 5 million observations, 200 features. And what we can expect with this fixed data set, ideally you want the runtime to linearly decrease. You can see it's almost linear. If I use more data set, more observations, I will probably get even more linear decrease of execution time. That's what happens when you design algorithm with thinking of distributed processing in mind. Specifically, distributed processing in mind, you typically want specific algorithms that minimize the amount of data transfer between nodes, right? So in particular, this k-means algorithm was designed to minimize data transfer between nodes. The most powerful communication avoiding algorithm uses schemas like MapReduce. Ideally, you want everything to be MapReduce. Sometimes you cannot do MapReduce paradigm. But in case of k-means, it's possible. The other example is linear regression training. The same blue chart, we fix it, input size, data set, 48 million observations, 256 features. And again, linear decrease in execution time. The other way how you can measure the scalability, you can double the problem size and double the number of nodes you compute on. And by doubling this, you still can expect the constant execution time. So you want this yellow and orange to be as close to horizontal line as possible. In our case, you see it's more or less constant, which again illustrates high scalability of these algorithms. Like with Berkeley Labs, we wanted to scale this to hundreds of thousands of nodes, cores. This is the way how you can achieve this. And the last but not least, I touched the aspect mainly about machine learning library. You cannot expect any machine learning library to cover everything. Sometimes you need to write own kernels, own code. And remember, if you implement this in pure Python, it will kill performance. Don't code in pure Python by itself. You need to use some technologies that can help you to exploit parallelism. Even coding in simple using NumPy will give you much more flexibility to exploit parallelism than coding with pure Python. The reason for that, NumPy is array programming. You manipulate on arrays, which means you can effectively extract instruction-level parallelism. Since it's array programming, it's well suited for element-wise operations on vectors. So you can use SIMD, and you can use multiple cores. You can do threading with different ways. So use NumPy, don't use pure Python. Then you can use technologies like Cython. OK, I coded in NumPy. The code still runs slowly. What can I do? I can use Cython, for example. Cython allows you to translate your Python code into native code with GCC compiler, for example. And then you can execute this hotspot as a native code. Or you can use the technologies like Number. Number is just-in-time compiler. If you know your Python code is slow, you can accelerate it with Number. Performance numbers. Red and orange. This is stock Python. We used Black-Scholes benchmark to illustrate this. So you see pretty low numbers, orange and red. And in contrast, you have the best C implementation or C++ implementation. So it's a green line. The light blue line is what if you implement this code with NumPy. You see it's much faster with optimized NumPy that we do with Intel distribution for Python than it was in stock NumPy. But the performance is much, much bigger if you use Number. It's really, really close to C implementation. It means you don't need to recode everything in C. You can still use Python, but with Number, you can decorate this kernel and execute. And having your data size, custom data transformation, or custom optimization kernel implemented in Number get still very efficient code. OK. Essentially, to conclude, I was talking about Intel Data Analytics Library. I was talking about Intel Python. But in fact, these are all open source things. Don't think about this as a proprietary something. What we're doing, we work with different vendors. We work with Anaconda. We work with other Python vendors just to enable these Python distributions with optimizations. You don't need to switch to Intel Python. You can use Anaconda and use our optimizations you can get through Anaconda Cloud, for example. In parallel, we also upstream this to open source. It takes time, but in general, all optimizations that we put in Intel Python product, they eventually go to their mother projects. Thank you.